Alkanes are found in fuels, crude oil, and many of the materials we use in everyday life. But chemically, they are surprisingly simple molecules. So what is it about their structure that gives them their characteristic properties, but also makes them relatively unreactive? To answer that, in this video we're going to look at what alkanes are and how their structure affects their properties and reactivity. But first, what exactly are alkanes? Alkanes are a homologous series of compounds that have the general formula CnH2n+2, where N represents the number of carbon atoms in the molecule. This means that every alkane will have twice as many hydrogen atoms plus 2 as it does carbon atoms. All alkanes also belong to a group of compounds called hydrocarbons. A hydrocarbon is a compound that contains carbon and hydrogen atoms only. This is a really important definition and one you need to learn word for word. It's an easy 1 mark in an exam that you can't afford to drop. Now, the key part of this definition is that it's a molecule that only contains carbon and hydrogen atoms. So whilst methane would be a hydrocarbon, a molecule such as ethanol wouldn't. Ethanol absolutely contains carbon and hydrogen atoms, however, it also contains an oxygen atom, which means it cannot be classified as a hydrocarbon as it doesn't only contain carbon and hydrogen atoms. Another important feature of alkanes is that they are saturated hydrocarbons. A saturated compound contains single bonds only, and again this is another important definition that you must learn. Now, mark schemes do allow you to say that a substance is saturated because it doesn't contain double bonds, but I don't really like this definition as it falls short pretty quickly. Alkynes are a group of hydrocarbons that contain a carbon-carbon triple bond. They don't contain a double bond, but they are still unsaturated. So saying a substance is saturated because it doesn't contain a double bond doesn't really work. I would therefore suggest always going with the definition that saturated molecules only contain single bonds, as it's more accurate. So alkanes can be described as a homologous series of saturated hydrocarbons, with the general formula CnH2n+2. And it's precisely because of this that alkanes have the properties they do. But before we look at the properties of alkanes, we need to make sure we can recognise and name these molecules. Now, this video isn't going to teach you the full IUPAC naming rules. That's already been covered in a separate video. But what we do need to look at is applying those rules to naming alkanes whilst being mindful of the common mistakes that students make when doing so. So let's play a quick game of Name That Compound. So before we start, remember the key steps. Identify the longest continuous carbon chain, number it to give the lowest locant numbers possible, and then add any prefixes in alphabetical order, remembering to add on any di, tri, or tetra prefixes where necessary. So let's take a look at molecule 1. So here our longest carbon chain is 4 carbons. It doesn't matter whether we take the straight line or the bent chain, they're both the same length. The methyl group is attached to the second carbon atom as I want it to have the lowest number possible, and 2 is lower than 3. Combining everything together gives me 2-methylbutane. Now, if someone's going to make a mistake on this one, it's likely to be the locant numbering, giving 3-methylbutane instead. Remember, we always number the chain to give the lowest locant numbers possible. Molecule 2. Now, this one's a tricky little number. A lot of students are going to instantly be drawn to that horizontal chain of 5 carbons and say you've got an ethyl group on the second carbon and a methyl group on the third, but they'd be wrong. Our longest chain actually includes that ethyl group, giving me a carbon chain length of 6. We've then got 2 methyl groups, and whichever way we numbered the chain, they'd be on the third and fourth carbon, giving us 3,4-dimethylhexane. If you get a question on naming alkanes in your exam, it's highly likely to be something like this, where the longest chain isn't going straight across. Examiners know this catches students out, and they desperately want you to fall into their trap. Well, how about molecule 3? Well, this one's got a variety of different routes we could take to get the longest chain, but they all give us a longest chain of 5 carbon atoms. Now, the thing we need to remember here is that we want to give as many of those methyl side chains the lowest number we possibly can. That means we need to number right to left to give us 2,2,4-trimethylpentane. Common mistakes on this would be going with 2,4,4-trimethylpentane, or possibly forgetting the tri prefix and just going with 2,2,4-methylpentane. And last but not least, let's have a look at molecule 4. Another one where you're desperately trying to make sure you don't get caught out by not finding the longest chain. But despite trying a number of permutations, the longest chain is just the 5 carbons. Numbering, I want the side chains to have the lowest numbers possible, giving me 3-ethyl-2-methylpentane, not 2-methyl-3-ethylpentane. Remember, our prefixes go in alphabetical order, not number order. This is another one of those easy mistakes students often make. Make sure you know your IUPAC naming rules upside down and inside out so that you can apply them consistently each and every time. Now that we can recognise and name alkanes, let's start looking at some of their physical properties. And we'll start with looking at how the boiling points of alkanes change with the size of their molecules. Looking at this graph, we can clearly see that as the size of the molecule increases, so does the boiling point of the alkane. Now, it's really important for you to be able to explain why it is this happens. Alkanes are simple molecular compounds, which means that although the covalent bonds within each molecule are very strong, we aren't breaking those covalent bonds. Instead, we are overcoming the weak intermolecular forces of attraction that exist between the molecules. These intermolecular forces are known as van der Waals forces, and as the size of the molecule increases, so does the number of van der Waals forces of attraction between the molecules, meaning more energy, and therefore higher temperatures, are needed to overcome them. So as the length of the carbon chain increases, so does the size of the molecule, which means there are a greater number of van der Waals forces of attraction between the molecules, which require more energy to overcome, and so the boiling point increases. Now, something to bear in mind is that some mark schemes require you to state that the van der Waals forces act between the molecules. You can tell this as it's underlined in the mark scheme. So although you may know that van der Waals forces of attraction are intermolecular forces and therefore do act between the molecules, you must remember to show the examiner that you know that. Now, the size of the molecules themselves isn't the only thing that affects boiling point. The shape of the molecule matters as well. Straight chain alkanes generally have higher boiling points than their branched chain isomers. This is because straight chain molecules can pack together more closely, giving a greater surface area of contact between neighbouring molecules. That allows more van der Waals forces to act between the molecules, giving a higher boiling point. Branched molecules are more compact, so they don't pack together as effectively, meaning fewer van der Waals forces of attraction act between them, and so less energy is required to overcome them, giving a lower boiling point than their straight chain equivalents. Another physical property you need to be aware of is that alkanes are insoluble in water, and you might have seen this when testing alkanes and alkenes with bromine water. They form an immiscible layer on top of the aqueous bromine water. The reason for their insolubility in water comes down to their polarity, or rather a lack of polarity. Carbon and hydrogen both have very similar electronegativity values, making the carbon-hydrogen bond essentially non-polar. As a result, alkane molecules themselves are also non-polar. Water, on the other hand, is a polar molecule. The hydrogen atoms have a partial positive charge, and the oxygen atom has a partial negative charge. And because polar and non-polar substances don't mix effectively, alkanes are insoluble in water. Now let's turn our attention to the chemical properties of alkanes. Earlier in this video, I described alkanes as being relatively unreactive. But what is it about alkanes that makes this true? Well, the answer lies in their bonding. Alkanes only contain carbon-carbon and carbon-hydrogen single bonds. And both of these bonds are really quite strong covalent bonds, meaning that a significant amount of energy is required to break them. So because these bonds are so strong, alkane molecules are generally unreactive. Those carbon-carbon and carbon-hydrogen bonds just aren't broken easily. And if the bonds in your reactants aren't being broken, the reaction simply isn't going to happen. The lack of polarity in alkane molecules also contributes to this low reactivity. Since carbon and hydrogen have similar electronegativity values, the bonds within alkane molecules are essentially non-polar. This means there are no significant areas of positive or negative charge to attract nucleophiles or electrophiles, making it more difficult for reactions to take place. And don't worry too much about the terms nucleophile and electrophile yet. For now, we'll just consider them as molecules or ions that are attracted towards positive or negative charge. And all of this actually links back to one of the definitions we looked at earlier. Alkanes are saturated molecules because they only contain single bonds. Compare them with alkenes, which contain a carbon-carbon double bond, and you'll see that the presence of that double bond dramatically changes the reactivity of the molecules and allows alkenes to undergo reactions that alkanes simply can't. But don't make the mistake of thinking that alkanes never react. They absolutely do. They're incredibly good fuels because they readily undergo combustion reactions, releasing large amounts of energy per gram of fuel. And alkanes will also react with halogens to form halogenoalkanes under the right conditions, and we'll be looking at those reactions in another video. But compared to many other organic compounds, alkanes are relatively unreactive, and it's their strong, non-polar bonds that makes that the case. So let's summarise what we've covered. Alkanes are a homologous series of saturated hydrocarbons with the general formula CnH2n+2. Their boiling points increase with the size of the molecule, but decrease when branching occurs. Alkanes are insoluble in water and are amongst some of the least reactive organic molecules due to the strength of carbon-carbon and carbon-hydrogen bonds. However, alkanes do make exceptionally good fuels because of the amount of energy they release per gram. In the next video in this alkanes topic, we'll build directly on what we've covered today by looking at crude oil and how the difference in boiling point between alkanes allow them to be separated by fractional distillation. As always, the full topic playlist is on the screen, and please feel free to subscribe for continued support with A-Level Chemistry.